So hey, I'm back and I'm super excited to tell you about this new performance study we just finished. It comes hot on the heels of the recent Spark 2.1 release, and it's a SQL on Hadoop running TPC DS workload, what we call Hadoop DS. And as you know by now, I am super hot on SQL for Hadoop, so let's begin. So first, let me talk about what is TPC DS for those who don't know. TPC stands for the Transaction Processing Council. And they're this independent, not-for-profit organization that's been around for decades, and it's vendor independent. That's really important. What they do is they define these different benchmarks that are industry-driven. And so in this case, it's based on a retail example. It's for DS, or decision support, and it mimics a retail business that has retail sales, web sales, so multi-channel. It's got inventory data, demographics, and promotions. On top of that, they define different kinds of decision support workloads that a typical retail business would run, such as reporting, iterative OLAP, data mining, and ad hoc. Now, these queries are predefined, and that's really important to understand. To keep things fair between testing different kinds of technologies, the benchmark prescribes that you have to run these queries as is, and it's up to the SQL engine to optimize and decide how to execute those queries. And then finally, there's different scales that are available for this test. 100 gigabyte, 300 gigabyte, 1 terabyte, all the way up to 100 terabytes. So the question we want to ask, of course, is what's the best solution for analytical SQL on Hadoop? As you know, there's different kinds of workloads that we can do. For Phoenix, for example, that's SQL over HBase, so that would be more of a transactional lookup type workload. For Hive and Impala, they're trying to do more analytical SQL as well as batch processing. And Spark, well, what is that going to be good for? And that's really the objective of this test. So let's take a moment to recap what we learned in 2016. Around the middle of last year, Radiant Advisors had released this benchmark that was sponsored by Teradata to test different SQL engines for Hadoop. And what makes this relevant to what I'm about to show you is that they also tested the 99 queries. And what they found was that at the 1 terabyte benchmark level, for example, that different SQL engines would have different abilities to run those 99 queries. In this case, Presto was the best at being able to run 75 of the 99 queries, and Impala was only able to run 62 of those queries. Now, the reason why this is important, of course, is that if we're thinking about moving some BI workloads to Hadoop, going to take some workloads from there and bring it into the Hadoop world, well, am I going to have to rewrite those queries, or will they be able to run out of box, and will they be able to run efficiently? So that's really the purpose of this test. If we roll forward the calendar just a little bit to late last year, you'll see that the benchmarks direct from Cloudera and Hortonworks, for example, and these are public blogs, they weren't much better. I mean, we see that there are some pretty bold claims here, like 25 times faster or 4.3 times faster, and so on, but they're often just running they're just measuring the improvements in performance over that subset of queries. So in the July one, where they talked about LLAP, for example, it was a 15 query subset for that 25x speed up. There's no mention of what about the other 80 or so queries. It's important to take these performance benchmarks with a grain of salt and understand the full scope. Are they running all the queries, and are they running them unmodified? And at what scale as well? You can see here they're running 1 terabyte, 3 terabyte. So the scale factor is important. But there's good news. Spark, as of 2.x, now runs all 99 TPC DS queries. Now, Spark is quite young, and you might be wondering, why is it that Spark has now leapfrogged all these other SQL engines for Hadoop? Well, part of it is because of IBM's contributions in this space. You can see here that actually, aside from Databricks, which have the founders of Spark themselves, IBM was the second largest contributor to Spark overall in Spark 2.0. In fact, there's more contributions from IBM in Spark than the next 5 vendors combined. And you can see that of those contributions, we're contributing across the stack, but we're really focused on 2 key areas, and that is in SQL and machine learning. So here we are now in 2017, and Spark 2.1 was just released. And once again, IBM is making a lot of contributions to Spark. We asked ourselves, what would it take to run a 100 terabyte scale benchmark to run those 99 TPC DS queries? Keep in mind, this is by far the most complete benchmark by any vendor for SQL on Hadoop, with roughly 10 times more data than anyone else. And this 100 terabyte benchmark is really big data. It's more than 500 billion rows. It's multiple fact tables with fact-to-fact joins. You can see the data distribution here. And so this is a very, very challenging workload. So we work with our partners in Intel and Lenovo to really engineer a system that would give Spark every advantage to hit this goal. And so we called this the F1 Spark SQL cluster. This was built with 28 nodes with Lenovo X3640 M5s. Each server was configured 2 sockets with 18 cores a socket, 1.5 terabytes of RAM, and racked up with SSD drives. But the cool thing about this was that despite the scale factor of the benchmark, this is running on just 2 racks, 28 nodes. And this cluster is connected with a 100 gig E 32-port Mellanox switch. So here are the results. To run this massive benchmark, it took almost 2 days at 43 hours. And despite our best efforts, unfortunately, we couldn't get all 99 queries working, but we did get 83 running with concurrency. And keep in mind that this number, while we didn't get 99 queries, it is better than any result of any other open source SQL engine. And I think we're fairly satisfied that we did everything we could to make this cluster run fast. You can see that the average CPU utilization across the cluster was fairly well balanced. And you can see that the average memory usage was pretty much maxed out around 75–80%. So we're confident we squeezed everything we could out of this cluster. Now my next question to you is this a good result? How will we know if no other SQL engine could even come close to this? What other query engine can run all TPC DS queries? Well, Big SQL also runs TPC DS queries. Let's try that. So that's what we did. We took Big SQL and deployed it on the exact same hardware as we had for the Spark SQL cluster. Now, before I get into the results, we want to call some pretty big differences right out the gate. Aside from performance, we know that Spark SQL can run all 99 TPC DS queries at 1 gigabyte and 1 terabyte, but as we got to 10 terabytes, we would start to get failures, and that's what we presented at Spark Summit. Big SQL, on the other hand, was able to successfully execute all 99 queries at all scale factors up to and including 100 terabytes. And actually, we've been doing this since October 2014. Now, I'm going to show you that Big SQL actually ended up being faster. But I want to take you through some of the details in the data to help you understand why, okay? And just looking at CPU utilization, for example, this is the CPU profile for the entire workload. We can see that the Big SQL side on the left, the average CPU utilization was 76.4. Meanwhile, for Spark, it was 88.2. So Spark actually had higher utilization. But if you look at the system CPU, and this is more about a measurement of efficiency of managing processes and operating system type tasks, the Spark SQL workload actually required almost 3 times more system CPU. What's special about system CPU is that it takes up time on the CPU, but it doesn't actually do anything useful in terms of completing work. So we consider system CPU as wasted CPU cycles. From an I/O perspective, this is the I/O profile for Big SQL versus Spark SQL. You can see that actually Big SQL does far less I/O for the entire workload. In fact, Spark SQL required 3.6 times more reads and almost 10 times more writes to complete that same workload. So this is a measure of efficiency of our query execution, how many times we have to go back to disk. And this is kind of shocking when you think about, well, Spark is an in-memory compute system. Yes, that's true, but it still has to go to disk to get data. Now, another way that we can view I/O is to look at max I/O rates. And max I/O rates is a good measurement of how hard the system can drive I/O. When we need to go to disk, how hard can we request data from those drives? And you can see here that for both reads and writes, Big SQL is far more efficient at getting data from disk. In fact, at peak I/O, we can drive nearly 2 times more data throughput from the same disk drives. And here are the results. Turned out with all those efficiency differences in I/O profile and CPU efficiency, that Big SQL was more than 3 times faster than Spark SQL 2.1. Now this performance result is based on comparing the 83 queries that both SQL engines could execute. But even then, when we compared 99 queries for Big SQL, that includes the 16 most challenging and difficult queries, versus just the 83 that Spark could run, Big SQL was still almost 2 times as fast. And so this was really surprising even to us. But then we even thought to ourselves, wait a sec, was that the whole story? Let's do some math here. Remember that the average CPU utilization was 76.4 for Big SQL, whereas it was 88.2 for Spark. But Spark ran for 3.2 times longer. So actually, Spark SQL actually takes 3 times more CPU time to complete the same workload. And remember that system CPU, which is like wasted CPU cycles? It was already 3 times worse compared to Big SQL. But if it ran for 3 times longer, that's like 9 times worse system CPU. Now let's look at those writes again. We know that Spark SQL required a lot more I/O than Big SQL to do the same amount of work. But again, it ran 3 times longer. And so this, doing the math, means that Spark was actually doing 12 times more data reads and 30 times more data writes. This is why Big SQL was outperforming. And the best part is, Big SQL, we think, still has a ton of potential here. Because what I didn't show you was this. Big SQL only used 1/3 of the memory on that cluster. It's crazy. Look at Spark SQL. It's using almost 80% of the memory, and we're using less than half easily. And so this means that you can have much smaller nodes in terms of memory footprint to do the same amount of work. Or maybe you can have that memory available to do other Hadoop workloads. So here's a nice slide put together by our performance teams comparing at a glance what it was like running Big SQL and Spark SQL on the same hardware running the same workload. You can see that instead of taking about 2 days, it took about half a day to get that workload done at 13.7 hours. We got 99 queries working, whereas Spark SQL, the best we could do was 83 queries. Big SQL is using 3.7 times less CPU. It's reading 12 times less data. It's writing 30 times less data to get the same work done. We're using the same Parquet formats, so that's saving 60% of space for both SQL engines. And you can see that the average CPU utilization for Big SQL is around 76.4%. But I want to make it really clear that this is not about Spark SQL versus Big SQL. It really is a performance study, and the technology keeps evolving. And I think actually that we got to think about it as Big SQL and Spark together is a really great combination. What we really have to think about is to make sure that we use the right tool for the right job. Think about how Big SQL could run all those 99 queries where lots of other open source engines can't. And Spark is starting to, but at lower scales. If you're thinking of migrating existing workloads to Hadoop, you want to probably use Big SQL here. If you want advanced security, you're probably going to want Big SQL because there's very limited security capability in Spark. On top of that, if you want lots of concurrent users, we've got an advanced workload manager in Big SQL that other SQL engines don't have. And we've shown you now that Big SQL does have best overall performance. But if I'm doing machine learning workloads, I'm building data pipelines, I'm using certainly simpler SQL, my data scientists are doing discovery, and there's lots of great features in Spark for that. I want really good performance out of box. Spark SQL is going to be a great choice. And so we can position these two together, reading over the same data sets. Not a problem. Hadoop is an open platform. And that's not all. Actually, Big SQL is a friend of Spark. Big SQL is the only engine that has really, truly deep integration with Spark. And I'm going to show you what this means. Here we see a picture of the Big SQL head node, which is where connections come in. And we have the Big SQL workers executing on the data nodes. What we can do is have the Big SQL head node now invoke its own Spark driver program. And from that, we can actually have Spark executors also run on the data nodes and have parallel in-memory transfers of data sets between the Spark executors and the Big SQL workers. No other SQL engine can do this. It's phenomenal. And this just expands the number of use cases we can do with these two technologies together. So I'd like to finish off on why IBM for Advanced Analytical SQL. Well, as you can see, IBM is investing in both horses. We were the #2 contributor to Spark. We've done lots of work with Spark for TPC DS at an unprecedented 100 terabyte scale. But we can also see that it still has a way to go to catch up to things like Big SQL, which we continue to invest in as well. I showed you that Spark has already leapfrogged a whole bunch of other SQL engines for Hadoop. And so it's really become a 2-horse race. And when you choose IBM and work with us, you can get both today. Big SQL is available for the IBM Open Platform as well as the Hortonworks Data Platform. If you like what you saw and you want to see more, please subscribe. Thanks very much.